So in this video, we're going to have a look at similar shapes, and we wanted to know what they are, what does it mean for shapes to be similar to each other, and also how we can use the idea of similarity to find unknown lengths in shapes. And we'll extend that idea further later on by looking at areas and volumes, but for now we're just going to look at lengths or distances. So basically, what are similar shapes? Shapes are similar if they have the same basic shape. So if you had one shape which was a triangle, a similar shape would also have to be a triangle. It couldn't be a different shape. All the angles would need to be the same in the two different shapes for them to be similar to each other. And also the sides would need to be in the same ratio. So what I mean by that, for example, is that if I had one triangle here and then a bigger triangle like this, if they were going to be similar to each other, then if I multiplied that length by 2, it would need to be that I multiplied this length by 2 as well, right? This would need to be times by 2 to give this one, this would need to be times by 2 to get this one, and so on. That would need to be consistent. So essentially, it's kind of like one shape is just an enlargement of the other, not stretched or distorted in any way. So if we look at these triangles that I've got here, we want to know, are these triangles similar to each other or not? And what we can see is, for example, with the two red triangles, the height of this one is 4 and this one is 12, so it's been times by 3. And we want to check, is that consistent? Because if it is, then they are similar triangles. Well, the base was 3. That has also been times by 3 to get 9. So that's the same as we saw with the height. And the hypotenuse was 5. It's been times by 3 to get 15. So every single dimension has been times by 3, and therefore those triangles are similar to each other. We can also do it with triangles by looking at angles. So as long as all the angles are the same, then they will be similar to each other. Well, we know that the angles in a triangle add up to 180 degrees. So if this is 90 and this is 50, then the one at the top is going to have to be 40, because 90 plus 50 plus 40 makes 180. So if that's 40 there, and then if we do the same for the other triangle, we can see that we had 40 and 50, therefore this angle here will have to be 90. And so we can see that, yes, these two triangles have exactly the same angles in 90, 50, and 40, and therefore they are similar triangles. What we might sometimes find is that our triangles have been rotated or reflected, but they can still be similar. They don't have to have the same orientation to be similar to each other. So again, we can just do our check and see were the angles the same, and if they were, then they would be considered to be similar triangles. So with this one, I've got 90 and 65 in the big triangle there. Add those together is going to give me 155, and so I'm going to get 25 degrees as the remaining angle to make them add up to 180. I can see on the other triangle that that missing angle will also be 65 degrees. So actually, if I look at those triangles, they both have the same angles in them, and they must be similar. Now, if I was going to try and then work with these triangles a little bit later on, we'll see the calculations that we might want to do with similar triangles. I would recommend actually redrawing them. So maybe the big one, I'll sketch it out like this and say, right, that's 90, and that's 65, and that's 25. And the smaller one, I'll do the same, because it's much easier to deal with them if they're in the same orientation, because you can see that that side, for example, corresponds to that side there. If they're in a different orientation, that can be quite hard to do. So that would be my recommendation, is that if you've got an awkward layout, just redraw the triangles so that they're the right way up, and then it's much easier to work with. Okay, so let's look at a sample question. We've got two ovals here, and we have been told that these ovals are similar. So we haven't got enough information to actually prove that they're similar for ourselves, but we've been told they're similar, so we know that there must be a constant scale factor that the dimensions of these ovals are being multiplied by to go from the small blue one to the bigger yellow one. And our goal is to figure out what's the height of this yellow oval on the right-hand side. So to do that, I want to look at the dimensions that I can see on both of the shapes. I can see the width of the blue one is 3 and the width of the yellow one is 7.2. So I can figure out what the blue one must have been multiplied by to get to the yellow one. The letter that we tend to use, that you'll see in a lot of textbooks and stuff, for the scale factor is the letter K. I'm not sure why, but that's the letter that's often used. So what I want to do is think about the fact that every dimension has been multiplied by this number K to get onto the bigger oval, and I want to figure out what that value of K is. What is that scale factor? So the way I could say that is I could say that 3 has been multiplied by the scale factor k, and it ended up giving me 7.2. So what is the value of k? K is going to be equal to 7.2 divided by 3, and that's going to be equal to 2.4. So basically everything, I can now replace that. That has been times by 2.4. Everything in that smaller oval has been times by 2.4 to give the lengths in the bigger oval. And that must therefore be true as well of the height. That 5 there must have been times by 2.4 to give me the height of this other oval. So let's have a go at doing that. We're going to say that B, let's do that over here. So B is going to be equal to 5 times by the scale factor that we just found, which was 2.4. And that then gives me 12 centimetres. So I know that the height of that yellow oval was 12 centimetres. We've got another one here, same sort of question, but you can see that that orientation is not so convenient this time round. So what I would be doing is I'd be looking at that those two triangles, and my first thing would be to try and draw them so that they're both kind of this way round. Right, I've already got the small one in that orientation, so I might just leave that one, then I don't have to do so much work. But that bigger one here, I'll try and spin it round so that I've got things in the right place. So what have we got? We've got a kind of 90-degree angle there. I should have labelled that. That's 90 degrees there. That's 90 degrees there. We've got a 50-degree. So let's put that in the bottom left of both of them. A little bit small over here. And then that's going to be kind of 40 at the top. The reason I'm writing those angles in is not because it's necessarily going to help me with the question, but because it's going to help me to put the lengths of this triangle in the right place. What I can see is that on the big triangle, that, let me just fill that in as being 40 as well, the length between the 50-degree angle and the 40-degree angle is 17 millimeters. So as a result, when I go onto my big triangle, I'm going to say that between the 50 and the 40, that must be the side that I wanted to use. That's going to be 17 millimeters. So let's fill that in, 17 millimeters there. Okay, the side between the 50 degrees and the 90 degrees, right, between the 50 degrees and the 90 degrees, that's 8 millimeters. So between the 50 and the 90 on my new triangle, that's going to be 8 millimeters as well. And the height of my triangle between the 40 and the 90, that's 15 millimeters. Let's do the smaller one. Obviously, that's already the correct orientation. So we've got A on the bottom and 6 millimeters is the height of that triangle. And that now helps me to see what corresponds to what, because I can see that the 15 and the 6, they correspond to each other, and the 8 and the A, they correspond to each other as well. The hypotenuse, although I was told it was 17 millimeters, but that's not going to actually be helpful for this question because I don't know anything about the hypotenuse of this shape and I've not been asked to work it out. So I can kind of ignore that. It's almost like a red herring, that information there. So I've just redrawn that a little bit neater so we can see it here with all those dimensions. I've spun that bigger triangle around, and we're going to use that to try and figure out how to work out the A value. So the first thing again is I want to work out K. What am I multiplying by to go from the big shape to the small shape? Now this time, obviously that's kind of a reduction. It's making the triangle smaller. So I'd expect that K value to actually be a fraction to indicate that lengths are going to get smaller rather than bigger. Alternatively, I guess you could work out the K value going this way around and then divide by that number rather than multiplying by that number. But I'm going to do it the way I've said at the bottom. So what happened? The information I know about is these two here. So I know that the 15 must have been multiplied by a number to give 6. So 15 times by K, the scale factor gave me 6. What's K equal to? 6 over 15. And that simplifies, doesn't it? 3 can divide into the top and the bottom to give me 2 over 5, 2/5, or 0.4. Now we can work out our A value because we've figured out that everything is being times by 0.4 or 2/5 to get to the smaller shape. So A is going to be equal to 8 times by 2/5. Let's just do it with fractions. Remember, if you're multiplying a whole number by a fraction, it can be useful to do it over 1 to remind yourself that you're just multiplying the numerators together and the denominators together. We don't want to multiply the top and the bottom by 8. That would be incorrect to do that. It also helps to see if any cancellations can happen between the top and the bottom, but 8 and 5, there's no common factors there. We can't cancel anything down. So 8 times 2, that's 16. 1 times 5 is 5. We could leave it like that, or I could write that if I wanted to as, how many times does 5 go into 16? It goes 3 times with remainder 1. So I could write 3 and 1/5 for my answer. So either would be acceptable there. Let's just do 2 more examples here. So we've got here some triangles that are, we're asked to show that they're similar. So we know that they are similar, but we need to explain why they are similar, and then we're going to work out the x and the y, as in the little x here and the little y there, the lengths that we've got to work out. So these ones are a little bit more involved because it's not maybe so obvious that this triangle here is similar to this triangle here without us doing some work. And this is actually a bit of geometry, like we talked about when we were doing trigonometry before. We know that this angle here is the same angle as that angle there. So that is the same as that one because they are what we call vertically opposite angles. So angle BXC is equal to angle AXD because they are vertically opposite angles which are always equal to each other. So we're aiming to try and prove that all angles are the same, and we've done that for now 1 pair of angles. That's not quite enough. We need to find a few more that are the same. But we can also see that this angle at A, I'm going to do 2 hoops there to show it's a different angle to the one I found at X. That's actually going to be the same as this angle over here because we've got what's called alternate angles. Alternate angles are always equal to each other when we've got parallel lines, and you can see we have got some parallel lines here. So what I can say is that angle DAX, that's equal to angle XCB because of what we call alternate angles are always equal. Now that's really enough because if 2 of the angles are the same in the triangles, the third one has to be, right? Because they add up to 180. So I know for a fact that that one there is going to be the same as that one there. I'll do 3 hoops there just to indicate again which ones go with which. These go with these, that one goes with that one, and that one goes with that one. Okay, so that's part A. We've shown that the triangles are similar. Now we're going to try and find out x and y. So again, what I'm going to do is I'm going to try and draw out these triangles in a better orientation because otherwise I could really easily go wrong. So let me maybe do the smaller triangle. So the smaller triangle maybe looks something like this. I'm going to do like sort of C, B, and X like that. There's all sorts of different orientations you could choose. That's what I'm going to go for. So I'm sort of showing which angles go with which. What do I know? I know that between X and B is 9 centimeters, so that's 9. And I know that between C and X, that's 6 centimeters, so that's 6 there. Now let's do the same, that's X, isn't it, between C and B. Let's do the big one. So the bigger one that we had there, what have we got? We know that we want to do the same orientation. So that double angle is at A, so I want to make sure that that's the same angle there and there, so that I've got the same bottom left corner. The angle at D is the one with 3 hoops, so that's D there, and the one at the top is X. So I've got the same orientation. Between A and X, that was called Y. Between D and X, that was 15, and between A and D, that's 10. Okay, so I want to try and figure out what x and y are equal to. What's the information that I can use to do that? Well, I know that this side and this side, they correspond to each other, and those are the ones where I've got 2 measurements. All the other ones, I've got x and 10, I've got 6 and y, that's not quite enough, but this one, I've actually got both bits of information, so I can work out what the scale factor is. K is being multiplied to 9 to get a value of 15 if I go from the small to the big. So K is 15 over 9. Again, I can divide the top and the bottom by 3. 5/3 or 1 2/3 is what everything is being multiplied by. That's going to unlock my question here. Let's do the first bit. What happens to work this out? The x, that's going the other way around, right? If I'm going from here to here and times in by k, if I want to go the other way, if I want to go this way, I must be dividing by k. So I'm going to do 10 divided by the k value, the 5/3, and that's the same as doing 10 times by 3/5, right? We turn the divide into a times and turn the second fraction upside down when we want to multiply fractions. So 10/5, that can cancel. That's a 2 and a 1. So what am I left with? 6/1, which is just 6. So the answer is that x is equal to 6, and we do have some units there, centimetres. Let's do the other one. To work out y, that must be this side and this side. So it's what am I timesing the 6 by to get the y value there. So y is equal to 6 times by the k value, which was 5/3. Let's cancel down. So the 6 and the 3 gives me a 2 and a 1. 2 times 5 is 10/1. 10/1 is just 10. So the answer is 10 centimetres for the y value. So that gives you a bit of an indication of how to work with lengths when we're dealing with similar shapes. You'll find that triangles come up more than any other type of shape with these questions, but it can be anything. And if we're told they're similar, we can apply these principles of having a constant scale factor that every dimension and length is being multiplied by.